a complex space that is just like Rk, except I do c to the k, I could also define a collection of complex numbers, right, whose dimension is going to be twice that of the real version if I thought about this as a vector space over R. But what does it mean? I could also define an inner product. And the inner product on CK, well, it should look something like this, except I might do something slightly different, just to be consistent with what we see over there. What would I do? Conjugate one of them, okay? So I'm just going to mention that it suggests in CK, which is basically collections of Z1 through ZK, Zi in C, the inner product. What inner product? Okay, well, I'm going to do the following. I'm going to, let's give the inner product a special symbol. In physics or quantum mechanics, you often use brackets. I know some of you are physics majors here. And we use the same notation. The bracket is an inner product, and I might take a vector. Now, here, the x and y are vectors of complex numbers. And then I will define, and this isn't in your book, by the way, I'm just telling you because I think you'll find it interesting. This inner product is what? Well, it'll be a sum of all the pieces xi, yi, I goes from 1 to k, but I'm going to conjugate one of them, the right one, okay, the one that's in the right argument. Okay, so this is a notion of inner product that you'll have on a complex space. Okay, and if I want, then I could talk about length in the natural way. When you take the inner product of something with itself, guess what? You get something positive, and that's because z dot z bar is going to be bigger than or equal to 0, right? So you get something non-negative. Okay. That's the reason for this. Okay. All right. Very good. We'll come back to this in a little bit because you'll see it'd be important for something we're about to do. But returning back to complex numbers, just one of them, if you have this length, there's lots of things you could verify about it. So let's do that here. And I'll either let you verify it. A lot of these things are very easy to show. So the property, so some properties you can show about this length. Sorry, let me box this because it's rather important. Clearly, the length is bigger than or equal to 0. What can I say about the length of the conjugate? Same thing, a squared plus b squared if it's a plus bi. Good. Okay. What can I say about the length of the length of a product? Yeah, and if the world is a just world, you might hope that this is the product of the lengths. Is it? Take a guess. How do people say yes? How do people say no? Yes, it is. Okay, but it's not altogether obvious. So the main ingredient in showing this is this rather remarkable number theory fact, okay, which says the following. So it's based on this rather remarkable fact in and of itself. Namely, if I take AC minus BD, square it, and add AD plus BC and square it, that turns out to be, just do the arithmetic, turns out to be the product of A squared plus B squared and C squared plus D squared. Okay, that's rather remarkable. And this, if you're a number theorist, is an interesting identity, because what it's saying is if you take the sum of two squares and something else that's the sum of two squares, and you take their product, guess what? You get something that's the sum of two squares. Okay, if these were integers. Okay. To an analyst, well, I don't care about integers, right? These are all just whatever they are, complex numbers, real numbers in this case, right? True. Oh, nice. Okay, so how does taking lengths play, does it play nice with the arithmetic? Well, for multiplication, it does. Okay. Okay. What about addition? Well, I should mention one more fact before we do that. The real part of z should be obvious that this is smaller than the length of z, just because it is the a, and you're comparing it. It's the side length compared to the hypotenuse. Right? Okay, let's see. Comma, 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 chameleon. No, sorry. And one more fact. How about z plus w? How's its length compare to length of z and the length of w? Yeah, enough of you have seen this. It's not the sum of the lengths, but it's smaller, less than or equal to the sum of the lengths. And this has a special name. It's a version of something we'll see later as called the triangle inequality. It's a version of the triangle inequality. And the reason it's a version of the triangle inequality, or the reason we call it that, is you could imagine these creatures, z as being a vector measured from the origin, and w being a vector also measured from the origin, but if I displace it to the endpoint of z, then this particular length, this dotted length here, that's the vector z plus w. And so the triangle part comes from noticing that one of the lengths, the z plus w length, it can't be longer than the sum of these two lengths, but it might be shorter because there's a triangle here. Okay? Okay, how do we show this? This isn't altogether obvious either. Why does the triangle inequality hold? We can do this. Well, let's just begin. I want the length of z plus w. I don't have a good way of dealing with the length, but I do have a good way of dealing with the length squared, right? Length squared is z dot z bar. In this case, the length squared is, help me, so this is one of those proofs that once you see the thing to start with is this, then it's easy enough. This is z plus w times what? Z bar plus w bar. It's the conjugate of the other thing, right? Oh, but what's this? I can multiply this out. Anybody can. This is z dot z bar. Yes? Oh, cool. Help me. Z dot z bar plus z dot what? W bar plus w dot z bar plus w dot w bar.